Okay, so in this video, we're going to talk about really like a review of inverse functions. So I assume you've heard of this, maybe you just forgot about it, so I'm going to try to just go through everything at a quicker pace. So you can't talk about reverse functions without first talking about one-to-one functions. So a function f of x is one-to-one if when a does not equal b, f of a does not equal f of b. Okay, so this definition might not make immediate sense. I always think the easiest way to think about this actually is visually. So I've discussed this diagram in previous videos. So functions in themselves have a very particular relationship. It's where one thing in the domain, so this is the domain, this first list, goes to exactly one thing in the range. So this can happen in a couple different ways. You can have one thing going to a unique thing, or you could have this is going to this and this is going to this. It's fine if two things in the domain go to the same thing in the range. That's just not going to be a one-to-one relationship. So these two little diagrams here both depict the idea of a function, but this diagram depicts a one-to-one function. And just to remind you, what would not be a function? So this first little set here, this domain, if one thing in the domain goes to two different things in the range, like you see here, this right here is what defines not a functional relationship. So functions are really just about like how one set of things gets mapped to another set of things, and one-to-one functions is a very specific type of relationship. So let's talk about, from a math perspective, how to tell whether you have a one-to-one function. So probably the easiest example of something that is not one-to-one actually is f of x equals x squared. So check this out. If I plug in -2, I get 4. And if I plug in 2, I get 4. So think about this from a mapping relationship. So kind of like how I was laying out here. So if I were to just draw a really crude little map, I have -2 and 2 both going to 4. And so that's exactly what I was talking about. That would not be one-to-one. So if you are given just a random function, you want to think of an example like this. What two numbers could I plug in? What two different numbers could I plug in to get the same like y coordinate, okay? Now, for example B here, this is like probably the standard example of what is one-to-one, like the easiest function we can think of that's one-to-one. So 2x plus 1, it's helpful if you know kind of something about the graph. What type of graph does this have? This would just be a line, right? This is in the mx plus b form. So this is just a line. And so any value that you plug in is going to have a unique y value. I can't think of an example that would work like this, right? So this would be, yes, one-to-one. And yeah, I think a lot of times the easiest way to think about this is whether you can think of the graph, or if you can think of, if you can't come up with any example that would work like this, then it's probably one-to-one. Okay, there is an easier way to tell a one-to-one function. I think that usually just having to like think through number pairs, that's always the hardest way to do it, but sometimes that's just what you got to do. But the easiest way to tell if you have a one-to-one function is the horizontal line test. So a function is one-to-one if every horizontal line intersects a graph at most once. So super simple. You might remember the vertical line test for functions. So let's talk about like, are these functions one-to-one? Okay, so I just brought up the vertical line test, so let's just confirm. So vertical line test, you go this way, right? And as long as these vertical lines only intersect the graph once, it's a function. So the horizontal line test just goes the other direction. And as long as the lines only intersect once, then it's one-to-one. So this would be one-to-one. Versus with this function here, I can draw a horizontal line. I intersect 3 times, so this would not be one-to-one. So the horizontal line test, kind of like the vertical line test, it just makes it so much simpler to figure this out. Now, the reason that we talk about one-to-one functions is that only one-to-one functions have inverses. So remember, we're reviewing inverses ultimately here. And just informally, just to kind of remind you what is an inverse function. So let's say that you have some function, it's a one-to-one function, and it's got the points x, y. So the inverse, which is denoted like this, f with this like -1 exponent of x. So this is not an exponent. This is literally a notation for an inverse. I know that can seem kind of annoying, but that's just the way that we do it. So what makes the inverse is literally all the points that you had x, y. Now you just flip the order of them to yx. So if you had 3, 4, now you have 4, 3 in the inverse. So that's like what kind of informally makes the inverse. So we want to talk about different ways to determine whether we have an inverse. So there's a couple different tests for this. So let's say that you have two functions and you want to determine if they're inverses. So we can use composition to determine that. So let f of x be a function and let g of x be its inverse. So look at this. F composed with g must equal x, and g composed with f must also equal x. Okay, so what does this mean? So it means that you have to compose the two functions and just see, you just want to check if this is the result you get. If you don't get this result, then they're not inverses. So let me show you an example of this. Okay, so I have this example. Determine if 2x minus 4 and 1/2 x plus 2 if these are inverses. So we're going to use composition to do this. So I'll review composition too in case you forgot it. Okay, so what it means to compose, so f of g of x, the literal definition of this is f of g of x. So it's always best to just rewrite the composition like you see here. And then with composition, you always want to work from the inside out. So the innermost function here is g of x. So this is my g of x. So I'm just going to replace it. F of 1/2 x plus 2. Now I look at my f of x, and where I see this x here, now I want to replace that x with this entire inside part. So I'm going to take that function 2x minus 4, but when I get to that x, I'm going to replace it with 1/2 x plus 2 like you see here. So notice how this is literally just 2x minus 4, except where the x was, I replaced it with g of x. And from here, now you just want to distribute and just like try to simplify this as much as possible. So just do whatever math you can. So in this case, I can easily distribute the 2. 2 times 1/2 x is x, and then 2 times 2 is 4, and then I've got the minus 4. And so this ultimately equals x. And so there is the result I was trying to get, x. Okay, we're not done. So now what we want to do is we want to do this again in the other order. So let me clear some space. And let's do it again, but now we're going to do g of f of x. And so this means g of f of x. So we're just going with the opposite order of the functions. Now, if you're watching this to review, I would highly recommend that you just try this on your own, especially if you're rusty on composition. There's a really good chance to practice this and to make sure you get it. Hit play when you're ready. Okay, so I'm going to start with the inside. So I've got 2x minus 4. So now I look at the g function. So here's where my x is. So I'm going to replace that x with 2x minus 4. So let's see, this is going to be 1/2 2x minus 4 plus 2. So now we distribute. So this becomes 1/2 times 2x is x, 1/2 times -4 is 2, plus 2, and look, we still get x. So yes, these are inverses. Okay, so that's how you use composition. Let's just try one more example, something that looks a little wackier here. So I've got 2 over x plus 6 and x plus 6 over 2. Now I would recommend at least just trying this first before you watch the solution and then hitting play when you get stuck or when you think you've got it. Okay, so I'm going to do the same thing. So f of g of x. So I'm going to take f of g of x. I'm going to just follow the same pattern. So I start from the inside, so I'm going to replace with this x plus 6 over 2. And now in my f function, I'm going to replace the x with this inside. So this will be, instead of x, now this is x plus 6 over 2 plus 6. So this does not look great, right? This looks like a little difficult. So how do we actually handle this? So what you'd want to do in this particular case to simplify this, the thing that makes this weird is that it has a fraction in it, right? So what I want to do is I want to get rid of the fraction. So I want to multiply both the top and bottom. Like this is a fraction within a larger fraction. So focusing on the little fraction here, I want to just multiply by the denominator. I want to multiply this by 2. I have to multiply the entire bottom by 2. And whatever I do to the bottom, I also have to do to the top, so that I don't change the value of this function. So now let's just investigate what happens. 2 times 2 on the top is 4. Okay, so now if I take x plus 6 over 2 times 2, the whole point of this, right, was for the denominators to cancel out. So then I'm just left with x plus 6. So that's x plus 6 times 2. And then I still have the plus 6 times the 2. So this is 6 times 2 is 12. And so what I get then is 4 over x plus 18. So that was not what we wanted, right? Remember, the whole point of this was to get the composition equal to x. And so since I have this crazy fraction here, I actually don't have to go any farther. I can just say these are not inverses. Okay. So the next thing I want to do is just talk about how do you actually find an inverse. So I thought this would be easiest if we just did it with an example. So I've got the function f of x equals 4x plus 2. Okay, so the first thing that you want to do is, if needed, you want to replace f of x with y. So I'm just going to restate this. F of x and y are often interchangeable, so I'm just going to restate it like that. The next thing you want to do is you want to flip, so wherever you have an x, you want to replace it with y, and wherever you have a y, you want to replace it with x. So just flip all to like the opposite variable. So this will become x equals 4y plus 2. Okay, so let me clear some space. Okay, and from here, what you want to do is you want to solve your equation now for y. So I have this x equals 4y plus 2. So just do whatever you have to do to solve for y. So what I'm going to do first is I'm going to subtract the 2. And then I'm going to divide everything by 4. And I like to write things in fractional form. So I would write this as 1/4 x minus 1/2. And then let me just clear a little more space. So the last thing you need to do now is just make a notation shift. So you want to just denote that this is the inverse. So remember, for the inverse, you have this like -1 symbol here. It looks like an exponent. So I would just restate this then as f inverse of x equals 1/4 x minus 1/2. Now, just if you were given y instead, so let's say this equation started out as y, so whatever variable you like solve for, you just want to denote that as an inverse. So you could write like y inverse here. That would also be fine. And again, you want to remember that this stands for inverse. So a lot of times you can look at this and say, oh, that means an exponent. But if we're specifically talking about inverses, then you just have to make that flip in your mind. Okay, so the next thing that I want to do is I just want to practice finding some inverses. So let's do a couple of these together. I would recommend pausing the video and just trying these. Remember, the explanation's always more meaningful if you try it on your own and get stuck versus if you just watch me do it. Okay, so I'm going to go through this. So first I'm going to replace f of x with y, and then I flip my x's and my y's. And then I just have to think, how do I solve for y? And this is where you can kind of get into the Wild West. So in this case, I have a cube root. So the only way I can get to y is if I cube both sides. So I'm going to just cube both sides. So I get 3y minus 1. Oops, sorry, plus 1. And then I can subtract off the 1. So I have 3y equals x cubed minus 1. And then I can divide all parts by 3. So ultimately, this is going to leave me with f inverse is equal to 1/3 x cubed minus 1/3. And so that would be my inverse in this case. Okay, so next I've got x plus 2 over x minus 1. So once again, like I think this can be a harder example. Math is not a spectator sport. You learn it best by being active with it. So I'd say give it a try and then hit play when you think you've got it. So I am gonna do what I need to do. So replace with y. And now here's the first thing. When you are replacing your x's and your y's, in this particular equation I have two x's, so I'm just going to replace them both with y's. So this becomes x equals y plus 2 over y minus 1. And now you've got to solve for y. Now this might look a little bit trickier, so you kind of have to think to yourself, okay, what's the issue here? So just in general with problem solving, when you have a fraction, you probably want to get rid of the fraction when you're trying to solve for something. So I might not totally know where I'm going, but I know that I probably don't want a fraction. So I'm going to just go ahead and multiply by the denominator so that I get x times y minus 1 equals y plus 2. Okay, now remember, the whole point of this is to ultimately get y by itself. So it would not make sense to try to just divide by x right now because you still have a y on the other side. You need the y's and the x's totally separated. So as odd as it might seem, I probably want to distribute the x just to see what happens. Sometimes you want to just mathematically explore a little bit. Okay, and the other thing that I want to do, so I'm trying to solve for y. So since I have just two y's here, I probably want to put these two y's together on the same side. I know that one of these has an xy in it, but we'll deal with that in a moment. Best practice is to get the variable that you're trying to solve for on the same side. The stuff that doesn't have y's, these are going to go to the other side. So I'm going to bring this y over here so that this becomes xy minus y. And then I'm going to take this x over to the other side so that I have 2 plus x. And now we're actually in the home stretch here. So now to finish solving for this, I am going to notice that on this side, both of these terms have a y in common. And the standard trick with that then is that you factor the y out. And now I can finish solving by dividing both sides by x minus 1 so that my inverse is actually equal to, well, actually the same thing, x plus 2 over x minus 1. So kind of crazy, but this function is its own inverse. So yes, it's a super exciting plot twist here in this video. Okay, so let's do one more. So this problem in and of itself actually probably seems similar to something we just did, but there's a little nuance to this last problem. So what I would recommend that you do is try to find the inverse, but also take a second to think about what nuance do you think I'm going to point out, and I will give you a big hint. It has to do with the domains. So give this a try, hit play when you're ready. So I have this function and I switch my x and my y, and so to solve this I need to just square both sides. So I have x squared equals y minus 5. So this seems pretty simple to solve. I just have the function x squared plus 5. So there's a big plot twist in this. What is the plot twist in this case? Okay, so I think you need to know a little bit about the graphs in this particular problem. So the graph of the square root of x minus 5 looks like this, right? Versus the graph of x squared plus 5 looks something like this. You have to know a little bit something about the graphs. And I know that we're reviewing this, so I'll just also tell you, like, the function, when you find the inverse function, it should still look like the original function. However, it should just look like it got, like, turned. And in this case, this does not look like the original function got turned. It looks like this function has a whole other extra arm, right? So this is kind of the last thing you have to think about. What's implied in the domain here of the original function, the domain of this goes from 5 to infinity. So it can't go below 0. If I plug in 4, for instance, I'll get the square root of -1, and that just won't work with inverses and finding domains and stuff. So domains have to be restricted to real numbers. Now, the domain of this function as it stands goes from negative infinity to infinity. So what we need to do is we actually need to restrict the domain so that these have the same domain, or so that they have the same, not the same domain, the same shape. So the other part of this that we have to think about is, what is the range? The range has to do with y values. So the range for this function, if I plug in 5's the lowest number I can plug in for this, right? So if 5 is the lowest number, I get 0. So this function starts at 0 and then it just continues on to infinity. Now, remember, the domain has to do with the x's. The range has to do with the y's. And we said that for an inverse, the inverse of a function just literally flip-flops the x's and the y's. So what I want to do then is I want to flip-flop the domain and range. So the domain in this case for this new function is going to be the range of my original function. So this domain needs to start at 0 and go to infinity. So I get like half a parabola, but that will align with the fact that this is like half a parabola that was like tipped over, right? So that is how we have to think about this. It's kind of rare that this comes up, but it does come up. So you do just want to think about sometimes domain and range, and if you need to make a restriction on it, it's kind of just implied in finding the inverse. So I feel like this is actually a great segue then to talk about how graphs relate to inverses. So if you know the graph, you know that two graphs are inverses of one another if they are a reflection over the line y equals x. So I think it's easiest to just visually go through this. Okay, so this black dotted line that you see here is the line y equals x, okay? And I have just two different functions here. So one function is in blue, the other function is in green. And all I want to know is just, are these two functions inverses of one another? So the way that you want to think about this at the dividing line. So let's take, for instance, this part of the graph right here. If I were to take this and fold it over, so think of this as a dividing line. If I were to fold this over, what would I get? So if I were to fold this right here, I would get this part of the graph here, okay? And then if I were to take this other part and fold it over the line, I can see visually how I would get the other part of the blue graph. So this first graph, these are inverses, okay? But what about this other one? So think about this. Now, if I were to flip this over this line, I would actually anticipate something. So you can even see here the point. So this right here is the point -1, -1, 0. So according to an inverse then, I should have the point 0, -1. I should have a point here. So I can tell just by looking at this that these are not inverses, because I already found one point where I've got the xy coordinate and I don't see the yx coordinate flipped. So these are not inverses. And visually you can maybe kind of project that in your mind. So I have just one more example here just to try to, bring this home for us. So I want to draw the inverse of this graph here. So what would that look like? So I think you really have to take this in pieces. So starting with this part of the graph, so if I were to just flip this part of the graph over this black dividing line, the dotted line is like the y equals x line. So if I were to just flip this graph over, I would have something that looks like this, right? Just starting with this piece here. And then this part of the graph, if I were to flip this over y equals x, then I would get this line here. So that is what an inverse should look like, and that's kind of how you get to it. So now you could see all these tricks to help you figure out how to get to your inverses. So that was your crash course review. Any questions, you can always leave a comment or DM it to me. And otherwise, I will talk to you guys in the next video. Thanks for watching.